Hello! Welcome to this series on the mathematical tools that underlie the Stat 110 lecture series. Today we're looking at binomial coefficients, which are a useful tool for counting the number of ways you can group items. Let's get started. So we're going to start where I like to start when I'm introduced to a new concept, and that's figuring out the name. You can skip ahead if this doesn't interest you, but I find this very helpful. If we look at this word bi means two in Latin. And then we look at this word nomial. Nomial means name or term in Latin. So we can take from this binomial two terms. Okay, so maybe like x and y. Now, similarly, coefficients. We've got co, which means together in Latin, and then efficiens, which is from efficiere, which means to produce, and that's Latin as well. And so together to produce, what this really means in maths is, say I might have a 5, and then I might have something else like an x, and together they produce something, so they might go into 5x, say. Taken all together, we can assume perhaps that we've got two terms, so I don't know, something like x plus y. And we're going to do something with these to produce coefficients. And that turns out to be correct. It's basically the terms that get produced when you do x plus y to the power of something. So we're going to end up with something like x to the n plus something, our coefficient, x to the n minus 1, y plus ... Okay, so let's talk about the purpose of binomial coefficients. First of all, you calculate a binomial coefficient by using notation like this, which you may already have seen. Now, what this means is I've got n items, and I want to know how many ways I can group k of them. So let's say I have, for example, A, B, C. So my n is equal to 3, and I want to know the number of ways I can group two of them. So my k is equal to 2. In this case, I would say, okay, I can get AB, I can get AC, and I can get BC. So there are 3 ways that I can group 3 items into groups of 2. Okay, so in this case, we would have 3, 2 is equal to 3. And the final important thing to remember is that nk counts the distinct groups. Okay? What that means is, if I have AB, and then I also have BA, there is no difference between these. They're equivalent. And this is the equivalent symbol in mathematics. So AB, BA is the same, and I only count these as one. This is one group, not 2 groups, because the order doesn't matter. Just like if you had 3 people in a group, it doesn't matter what order they stand in, they're still the same group of people. So let's talk about how the equation works. You've probably seen this before. nk is equal to n factorial over k factorial n minus k factorial. Now, this is the standard equation that you see all the time, but we're just going to talk about why it works. let's take a slightly more complex example than before. So rather than A, B, C, we'll say we have A, B, C, D, E, and F. So n equals 6. And I want to know the number of ways I can select 3 of them, say. So k equals 3. And I'm selecting without replacement. So that means if I select A, I can't reselect A. There's only one A. So if I look, I can see that I've got 1, 2, 3, 4, 5, 6 possibilities for my first selection. Let's say I do select A. Okay, so I've got A in my group. Now I can't get A, so we don't count A anymore. Left over, I have B, C, D, E, and F, a possibility of 5 different things. Let's say I select C. Okay, so now I've got left over B, can't have C, D, E, F. 4 possibilities. Let's say I select F. Okay, so there were 6 ways I could do this, times by 5 ways I can do that, times by 4 ways I could do that, and that equals 6 times 5, 30, times 4, 120 possible ways. But this actually isn't accurate because it's saying I care about permutations. Because I could still do, for example, F, C, A. So the inverse, and that counts as one of the 120 as well. So I'm actually overcounting the number of ways that I can group these together. To overcome this, we can say, well, how many ways can I arrange k items? How many ways can I arrange 3 things? So we can do the exact same thing as we did up here. And we can say, oh, okay, so there are 3 ways to arrange the first one. Then I get 2 choices. Then I get 1 choice. So I've got 6 ways of arranging 3 items. And so I can do 120 divided by 6 equals 20 possible ways to group 6 items into a group of 3. So we can generalize this now. So when we had n items, so 6 items, we saw that it was 6 times 5 times 4, because we were going up to 3, but say we went up to 2, for example, then it would be times 3. So we can see that we've got n times n minus 1 times n minus 2 times dot dot dot, which means we continue the sequence to n minus k plus 1. Okay? And then all of that was divided by k factorial. So we don't overcount the sequences we can get and stick to just the groups. Okay, so you can sort of see that this looks kind of like a factorial as well. This section here looks a bit like a factorial. And so if we wrote it out as a factorial, we would have n factorial divided by m minus k factorial. And the reason this works is I just want to go up to m minus k plus 1. And so if I had n minus 1 dot 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 n minus k plus 1, n minus k dot 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 all the way down to 1, then I know that if I have m minus k factorial, this section is taken out by this. So I'm still left with this, which is what I have up here. And that's why we end up with the m minus k. Okay, so that brings us back to the equation that I showed you initially. So you can see that's what we've got. We've got n factorial, k factorial, m minus k factorial. So let's show why this is powerful with an example. Imagine you're in a classroom and your teacher says, okay, I want you to divide yourselves in half. And because you love probability so much, your brain just starts going crazy thinking, well, how many possible ways are there to do that? And so we can answer that with binomial coefficients. Let's say there are 50 people in your class. If we wanted to divide the class into two, then we would have to choose 25 of the 50 people. And using binomial coefficients, we can calculate how many ways there would be to get a group of 25 out of 50. So, m factorial, 50 factorial, over k factorial, 25 factorial, over n minus k, 50 minus 25 factorial. And this gives us the value of 1.26 times 10 to the power of 14. Roughly speaking. I mean, there's a few more things off the end here, but roughly speaking. That's a lot of ways. And you find that the number of groupings you can get grows exponentially. Now, let's try a slightly thornier problem. So, imagine I have 10 sticks and I have 50 balls. The question is, how many ways are there for me to arrange these balls and sticks in a line? So one way would be like ball, stick, ball, ball, stick, ball, 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 stick, stick, ball, etc., until I've used up all of these. Okay? So what you could do is you could count the number of ways. Be like, oh, if I just draw this for a stick, I could do this and see how many times I could make an arrangement, but that would take an incredibly long time. And so this is not typically done. Instead what we can do is say, okay, well, when I run out of sticks, all the rest are going to be balls. Or when I run out of balls, all the rest are going to be sticks. So what I really want to know is, together, I have 60 possible items. And if I'm going to select either 10 of the sticks or 50 of the balls, and then I'm done, because all the rest will be sticks or all the rest will be balls, then the combinatoric calculation I want to do is the binomial coefficient for 60-10 or an equivalent for 60-50. And this is equal to 7.54 times 10 to the power of 10. Again, this is rounded. Okay, so I hope that helped you understand binomial coefficients and why they're very helpful for counting things, and even that they can be used for problems which are slightly more thorny like this if you use them creatively. See you in the next one.